Welcome to our third and final video from section 14.1, and the focus of this video is on the topic of level curves. So one way to help visualize a graph is by using level curves. So here's our formal definition. The level curves of a function f of two or more variables are the curves with equations f of x, y equals k, where k is a constant in the range of f. So to compute our level curves, we'll simply take the equation of our function and set it equal to a constant k. Now, the level curve f of x equals k is showing us where the graph of f has a height of k. So in other words, it's showing us where the surface is intersecting the plane z equals k. To get a better picture of this, let's hop over to GeoGebra. Okay, here we are in GeoGebra, and I have here a cone. Z equals the square root of x squared plus y squared, and we're going to find the level curves for this surface. So the picture is we want to think about what's happening as this surface is intersecting planes of various heights. So here's a plane z equals 2, here's z equals 5, and here's z equals 8. And so we can see there's our cone that has intersected these planes of various height. And so our level curves are just the shapes that we're getting as these planes intersect our cone. And so if we rotate around, we get a better picture and see that what's happening is our intersection between the horizontal plane and our cone is forming a circle. And the greater the height of the plane, the bigger the circle, right? So here is z equals 8. Here was the intersection with z equals 5 and the intersection with z equals 2, right? So the greater the height of the plane, the bigger that circle of intersection is going to be. And so when we go to sketch these level curves, in this example, the level curves will be circled. So here's our level curve for z equals 2, for z equals 5, and for z equals 8. And if I get rid of the three-dimensional piece of things and move us into the xy plane, then the level curves for this cone would look like this. They would look like these circles here. All right, let's compare that to the case where our surface is a plane. So I'm going to get rid of these guys. So here we have our surface is a plane. You can see it there, and we're going to intersect it with those same horizontal planes, z equals 2, z equals 5, and z equals 8. And in this case, you can see that those intersections are lines, right? So what we're getting when we intersect our plane, this pink plane, with our horizontal planes, z equals 2, z equals 5, and z equals 8, those intersections are lines. And so to help us picture what's happening here, so our level curves then, if we move into the xy plane, oops, there we go, sorry for rotating you around. So if we move into the xy plane, then our level curves for this example would just be lines. Great. Okay, here's another example. We have a surface that's kind of like an elliptic paraboloid, and so you can see places where if a horizontal plane intersected this surface, it will do so in a circle. And so then we take those circles of intersection and push them down into the xy plane, and that's where we get our level curves. And now all of the examples we've done so far, we started with the surface, we intersected it with the horizontal plane, and then pushed those intersection curves down into the xy plane. But you can also go backwards, right? So if you were given these level curves to begin with down here in our xy plane, if we took this circle and moved it up, we pulled it up to a height of 45, right? And then we took this circle and pulled it up to a height of 30 and so on and so forth, and pulled this curve up to a height of 20, then we could, starting with the level curves, we could recreate the function. So you can go in either direction. Here is another example where I just want to point out here's some surface z equals f of x, y. And so if we focus first on the quadrant where x and y are both positive, notice that maybe we have a big circle of intersection at around -10, and a much smaller circle is going to be as we move downward along the z-axis, so a plane of, say, z equals -100. And compare that to the quadrant where x is negative but y is positive. So here, if we intersect around the height z equals 10, we may get a big circle, and if we intersect around a height of, say, z equals 100, then we would get a much smaller circle. Great. Here's a real life example of a level curve. Sometimes these are also called a contour map. These show the contour of a mountain called Lonesome Mountain, right? So it would tell a hiker exactly what the terrain is going to look like to help them plan their hike. All right, let's do some examples that are a little bit different. So suppose we want to sketch the level curves of the function f of x y equals 8 minus 2x minus 4y. So what we'll do is use our definition. So the level curves, we're going to take our equation, 8 minus 2x minus 4y, and set it equal to a constant k. Now if we rearrange that equation to solve for y, we get minus 2x plus 8 minus k equals 4y. And then I'm going to divide by 4. So negative a half x plus 2 minus a fourth k equals y. And so what we're looking at here are equations of lines. So this is telling us that our level curves are lines. And for some specific examples, if k is 0, we would get the line y equals negative a half x plus 2. If k equals 4, we would have the line negative a half x plus 1. And if k is negative 4, we would get the line y equals negative a half x plus 3. And so to sketch the level curves, we would simply sketch those 3 lines. And notice this makes sense for our level curves because this is the equation of a plane. And as we saw earlier, the level curves for a plane are in fact lines. All right, let's do one more like that. Let's sketch the level curves of the function f of x y equals the square root of 16 minus y squared minus x squared. So to find the level curves, we take our equation and set it equal to a constant k. Notice in this case, because k is a positive square root, we automatically know k must be a value greater than or equal to 0. And if we square both sides of our equation, we see that k squared is 16 minus y squared minus x squared. Or we can rearrange to write x squared plus y squared equals 16 minus k squared. And when we write it that way, we observe that our level curves are circles. They're circles centered at the origin, in fact. And so for some specific examples, if k is 0, our level curve would be the circle x squared plus y squared equals 16. If k is the square root of 7, our level curve would be the circle x squared plus y squared equals 9. And if k is 4, then we get the point, actually, x squared plus y squared equals 0. And so to sketch our level curves, they would look like this. They would look like the circles that you see here. Again, this makes sense for an answer because our surface in this case is the top half of a sphere. And so it conceptually makes sense that if we slice that sphere with horizontal planes, that those intersecting curves are going to be circles. Here's an example where we have a contour map shown of a real life situation. We're going to use it to estimate the sea surface temperature for the following longitude, latitude points, starting with the point 205. So we want to find a longitude of 200, a latitude of 5, so we're looking at a point right about there, and we see that it's close to that line 27, but moving toward the 28, so just a little bit greater than 27. So we would estimate that the sea surface temperature for 205 is approximately, say, 27.1, a number just a little bit greater than 27. All right, what about at the point 230, 0? So we want to find the longitude line of 230 and latitude of 0. So we're looking at a point right about there. It's the point really close to that level curve of 24, but just a little bit smaller than 24. So we may estimate that the sea surface temperature at this point is, say, 23.9. So something just a little bit smaller than 24. All right, here's one final example. Here we want to match the functions A through E, those surfaces, with the contour maps 1 through 5. Before we dive in to this example, I would really encourage you to pause the video just a minute and practice yourself. See if you can match these surfaces with the contour maps. So pause the video, try it out, and then I'll walk you through my solutions and you can see if you came up with the same answers that I did. Okay, so to be strategic about it, I'm going to start with the surfaces whose level curves are going to be circles. So that will be A, D, and E, right? Those are the surfaces that when you slice them horizontally, those intersecting curves will be circles. Okay, so starting with A, we notice that as you slice going down the z-axis, you're going to be getting bigger and bigger circles, right? So as z becomes negative, you'll be getting bigger circles. And so that tells us that surface A goes with contour map 3. Okay, focusing on D next. The smallest circle is going to be kind of right around 0, and you'll be getting bigger and bigger circles as you slice higher and higher and higher. And so if we want bigger circles as we go higher, that tells us that D is going to match with contour map 2. And just to double check, in E, your smallest circle is going to be at your biggest elevation, and you're going to get bigger and bigger circles as you slice towards 0. And so sure enough, that makes sense for level curve 4. Okay, so now we just have to worry about our lines. So starting with B, so notice where Y is positive, that those slices are going to happen at elevations where z is negative. So where y is positive, those elevations are going to happen when z is negative. And so that tells us that plot B goes with number 1. And it makes sense then that C is going to go with 5 because we see that symmetry, right? The symmetry as well as the fact that those slices are going to be spreading out as you go down to lower elevations. Okay, so that's all for this video and all for our videos on section 14.1. Thanks so much, guys.